Okay, this is the video tutorial for chapter 7 of the textbook, Finite Element Essentials in 3D Experience 2021x. And the particular chapter that we're going to be doing is 7, namely a very simple truss analysis. So the problem under consideration is a three-member truss, 1, 2, 3, A, B, B, C, and C, and AC are truss members, and the supports are shown here. This support at C is at an inclined angle 45 degrees. So we have a load that is applied, concentrated force that is applied at the point B, and these members have two of them have square cross section 24 by 24, and the other one, the inclined member, I believe is a square 34 by 34 millimeters. Oh, right there, right there. Now, uh, in order to do the problem, I'm going to create 4 points, points 1, 2, 3. Point number 4 is not going to be useful for this problem, but when we repeat this thing as a frame problem, point number 4 becomes important. I'll create it here, but I will never use it for a truss problem. And so the geometry is shown there, and it's a standard steel properties, and the load is 1,000,000 Newton. Okay, so let's move on. All right. I am already in 3D Experience part design workbench. In this particular problem, it really doesn't matter whether you're in part design or generative shape design, because you're creating lines basically. So it really doesn't matter. So my first task is to create those 4 points. Okay. So under the essentials, this is how you create point number 1, coordinate 0, 0, 0. I think that's what it was, right? 0, 0, 0, 0, and then goes up, etc. So this is all happening in the x equal to 0 plane. Okay, so when it comes to typing in the coordinate, that helps to know. Okay, the second point, x is 0, but z is 1,000 millimeters up there. You can see that. Uh, let me see, for example, what are my units here? Actually, I may have inadvertently my units, I think, were in inches. So let me go ahead here. Yeah, so that's 1,000 millimeters. I'm going to change my units in a minute. Okay. Let me make sure everything is fit. Right there. There's a point, but I'm going to change the units. So preferences on the units, instead of inches, I want millimeters. And for force, let me actually change my unit of area too. So millimeter square. Okay. And then for force, we're going to use newtons. There. Okay. So the next point. Next point is going to be y of 1,000. This is not correct. This should be 1,000 millimeters. I have to fix all of these. Okay, so let me check my units. So point number 1, of course, 0, 0, 0, no problem. Point number 2, 1,000 up, 1,000 up millimeter. Okay, and point number 4, that's good. So let's fit everything, make sure that makes sense. So view, fit. Yeah, right there. So this is point 1, point 2, point 3, and point 4. I don't need it. So I'm not going to even bother doing it here. So that's fine. I'm not going to do that. All right. The next thing we want to do is to create the lines. So a line number 1, I believe, went from point 1 to point 2, etc. So line 1 goes from this point to that point. Line 2 is going to go from point 2 to point 3. And finally, line 3 is going to be that inclined line from here to here. Okay, so we created our points. Point number 4 is not created. Okay, so that's pretty much it. So let me also define my material properties. We already have that. It's properties of steel, but let me remind you how to do that. So you're going to say tools. Here is material, create material. Say okay. Forgot to give it a name. Did I give it a name? I think I forgot to call it something. Probably it's called material 1, the default value. So it was okay. So let me do it in the order, sort it in the order, descending order for date. The one that I just created must be the first one in the list, and I didn't give it a name. So I think it's this one probably, right? It's this one. Okay. All right. So let me double click on it. Let me right click simulations. It's structures, abacus multiphysics, mechanical, elastic. So this is going to be the units. Okay, what I change the units there to 200 e to the 6 e to the 9 uh, uh, Newton per meter squared. Okay, so I'll write it as PA, Pascal, which automatically converted to this. Okay, so and this is 0.3, 0.3. I forgot to change the units in my preferences, but then I typed it in Pascal, automatically converted it to PSI, which I didn't have to. Okay, now we can say right click apply. I'm going to close this. I'm going to apply it here and say okay. So let's see now. Material, that's this one. Better have the number that I just typed in. Yeah, it does. Okay, this is 200 gigapascal. Okay, good. All right, so this is it. As far as the model is concerned, that's all we need to do. The next thing that we're going to do is to uh, go ahead and create the mesh. Okay, so you have to go to structural model. Okay, say okay. Notice that the node and elements have not been automatic, or node element and properties have not been automatically created because there is no solid geometry here. Okay, so we have to go to let's select this under mesh. See that mesh? We have to decide what we're going to use. Obviously, we're going to use the truss element, or it's called B mesh, one-dimensional one. Okay, so notice that I'll start here, this vertical edge. And for the size of the mesh, I'll put down 2000 millimeter. And you might say, wait a minute, this whole thing was 1000 millimeters. So why are you putting 2000? Because all I need is a single mesh going from this point to that point, single element going there. That's why I put down 2000 to make sure that there's a single element over here. And then it's going to be the same thing there and there. Now, make sure that this box is check, capture, uh, make sure that the nodes are, yeah, so, yeah, right. So we put down, what this thing means, any two nodes that within 0.1 millimeter of each other is going to merge them. Okay, now notice that when I mesh this line, it's going to create two nodes on the top and the bottom. When I mesh the horizontal line over here, it's going to create another node at this point. And these things should be the same node, and therefore they have to be merged. And basically this tolerance will merge them, okay? So we say, if you just say mesh, it'll create the mesh right away. Otherwise, you have to do that later. So it create it. Let's do another one. In fact, bear with me for a second. So let's do this one. Again, 2000. This is the tolerance. Notice that it did create it. Let's do the other one. That's this. Yeah, so I'll put down here 2000 because that thing is about 3000. So yeah, that should do it. I need one element through this, so I think that'll do it. Yeah, it did it. Okay, so it did create the elements. If you want to see that, you can say right click, mesh visualization manager, and just show me the elements. Show hide the part. How about that? Hide the part. You can see the three elements have been created here. Okay, so let me put it back on. Show the part, and let me actually hide the mesh. Okay, good. We could have left it there. Yeah. All right, now, so the elements are created. There is three of them. You can see that. And then the properties. For properties, you have to go to, let's see now, to model. Here, we don't want mesh. We go to model right there. See that? Model. And under properties, we want this beam section, but we really don't want beam. These are not, this is a truss, so they're not beam elements. In reality, this is a link property. So notice that uh, all it does is asking for area. Okay, it doesn't care what the cross section looks like. All it wants is the area. So let's go ahead and start on this side. So this one, the area, well, if you go back to the area, here it was 24 by 24, which incidentally is 576. 576, so type in 576. 576. Say okay. And same thing with that one. Again, 576. 576 millimeters square, obviously. And this one is 1156. So that one is 1156. Good, the material is automatically picked because we assign that material to that steel material to the entire part. So these are all okay. If you want to update these, by the way, all you have to do is you click on this guy, update guy, and they're going to get updated. It's not a big deal. All right, so the one thing you want to do, and this is very important, remember I created 4 points here, hide them. Because some software, when you have a point and you apply a load or restraint to that location, some software, if they pick the point, they don't know that it actually is intended to be on the vertex, and they may not draw. Now, I'm not 100% sure here, so to be on the safe side, I'm going to hide these things, hide them. Okay, and yeah, line is okay, doesn't matter. So we are gonna go back to, we're done here. Oops. Okay, now we're gonna go to the, what is called the scenario. We're gonna go to scenario, okay? So we go to create a scenario. Where is that? Right here, structural scenario. We are doing a structural problem. Okay, notice that there's two exclamation marks which are red here. That's because we haven't picked our finite element model yet. We haven't picked this guy yet, okay? And we haven't specified the type of problem that we want to solve. Okay, so we go to setup. You have to select your finite element model. Right there, you click on this guy. And there's only one that's created. Remember, it's this one right there. So we select it and we say okay. Incidentally, you can create them if you haven't done it before, but we did create it before. Okay, good. Notice that this thing turned into a green check mark. And if you look at the cross section of this, it draws as a circle, but because these are link element, it's totally irrelevant. I mean, basically all link element are drawn as circle, but the actual shape doesn't matter. Okay, truss element. That's what I mean. Bar element. Okay. Now, what about the procedure? We want to do static analysis. This is static analysis. Okay. You click on it. This is a simple, straightforward linear problem. I don't have to do anything fancy. This is totally useless, so I'm going to uncheck it, by the way. There's no large deformations here. Okay, so we created, notice that this guy also turned green, which is a good sign. Okay, now we're going to apply our restraints. Okay, so we go to restraints. Okay, now this point on the top, first of all, if these are bothering me, I can always hide them. So these are probably properties, right click hide. Okay, good. Okay, so I put the cursor on this branch, right click and hit. Now hit it, hide it. And then one of them is, let's see now, the bottom one here is, this one is clamped, okay? So what we can do is we can go here and you select the clamp icon, and that point is clamped, okay? Before I do the rest of them, let me save this. Okay, this top one, see this top one? This top one does not move in the direction, if you look at this, it does not move in the direction X and Z, but it can move in the direction Y. So what we do, X and Z are fixed, Y is not. So let's go back here, and that's fixed displacement. So this particular point in that coordinate system does not move in the direction X and direction Z, okay, but it can move in direction Y. These rotations are totally irrelevant for truss elements. Truss elements have only translational degrees of freedom. You can check it or you can leave it unchecked. It really doesn't matter. And the axis coordinate system is the global according to this. This is all lined up with the global coordinate system. We say okay. Now this one, on the other hand, see this guy? This guy moves at a 45-degree orientation. You click on it and you select it. It puts a coordinate system there. But then what I need to do, I have to put one of these, line it up with that direction. Okay, so you can do rotate about the x-axis by minus 45. Okay, so x-axis by minus 45. Okay, yeah, that's good. Okay, very good. Uh, I I think in the book I actually created the coordinate system outside of this place, okay, and then used it. So that's why. So let's see now. This point moves along the z-axis, so it's prevented to moving in the x direction and the y direction. Okay, but it can move along z. Fine. You say all right. Okay, good. And the load is a concentrated force at that location. Now this is fine. The coordinate system that we have here is a default coordinate system. This is fine. and this is going to be pushed in the direction y by 1,000,000 Newton. I think that's what it was. 1, 2, 3, 4, 5, 6 Newton. Okay, there it is. You can see that. It's pointing to the right. You say, okay, right. So the only thing different between what I did in the tutorial, in the video, and what's in the book is probably the choice of this coordinate system. Here, I did it on the fly. I rotated that coordinate system so that it actually coincided with that line. And I think in the book, I must have created a coordinate system beforehand, and whose one of the lines was along, one of the axis direction was along that line, and then used it by picking it when I was doing the calculations. Okay, so this pretty much it. Let's save everything. Let's go ahead and simulate. First, check it, make sure everything is okay. Models work, and simulation check. Nothing fancy here. These are very simple problems. And I don't think I forgot anything. So let's go ahead. So far, no errors, no warnings. Maybe one warning. We're going to read it. Though sometimes these warnings, they don't say much. They tell you something that takes a, I don't know, it takes a genius to decipher. Don't worry about it. Let's run it and see whether it works or not. It's a bad strategy, but we'll see. Okay, so we are running it. So this is supposed to slide along that direction, along that support, and it's kind of hard to say. My guess is that it's going to go up. Yeah, my guess is that it's going to go up the ramp. Okay, good. Close that, and let's look at it from the front view. So view from the front, right there. And then this is the initial one without any load applied, and when you apply the load, it's going to go up. You can see that right there. Okay, this shows you von Mises stress, and you can do that. But if you want the deformation displacement, okay, so you get roughly 11 centimeter 11 centimeter goes up the ramp. Now if you want both of these to be present, now if you, this is for multi-plot, so you click on it, and then for example you can say also show me the original uh, undeformed model right there. See that this is the undeformed model, this is the deformation, and for von Mises stress, if you want, you can do that. Now what it does is that puts everything on top of each other, right? Because you said multi-plot, so it put displacement on top of undeformed shape, and the legends also, they put it on top of each other. So, oh, oops, yeah, one of them is for von Mises stress. You click on it, you drag it right there, and this one, you click on it, drag it, and when you're done, you click on it again, and you've got all three of them. Okay. Now, von Mises stress for a bar makes sense. For a link, it makes sense because it doesn't matter where in the along the at what cross section you look at. But when you have a frame element and it's bending, then the von Mises stress is not at a single location along the bar. Is not a single value, depending on what location on the frame you're looking at, cross section you're looking at, and that's it. Have fun. The next one I'm going to do is going to be chapter, I believe, 8, which is the same problem, except that it's going to be done in as a frame problem. In that problem, I'm going to create the local coordinate system first and then use it. Okay, here I did it on the fly though. Good luck.